LTR does not fail on models. It fails on data. This fixes the data pipeline. By the end of this video, you will understand how to turn search feature logs and clicks into a clean training dataset for OpenSearch LTR. I'm Professor Pi, teaching search and IR with simple Python. We will build a tiny, honest pipeline that indexes 3 documents, logs per document features for a query, attaches simple click labels, and exports a LIBSVM style training set so you can train a ranker. This snippet establishes an OpenSearch connection using the official opensearch-py OpenSearch client and creates a minimal dataset. The variable client points at a local cluster, which keeps the setup simple and reproducible. 3 documents are indexed into the docs index, each carrying a title for textual relevance and a pop field for a simple behavioral or popularity signal. The indices.refresh call makes the newly indexed documents immediately searchable. The final print confirms how many documents are present, ensuring the foundation for later feature logging and training data assembly is correct. Seeing indexed docs equals 3 means our toy corpus is ready to query and instrument. Search quality often breaks not because the model is wrong, but because the data you feed it mixes formats or drops the user signal. In practice, you want training rows where each candidate has the same features, a label that reflects user behavior, and a clear query ID. That is what OpenSearch LTR with feature logging and click joins gives you. It removes manual feature extraction and ties what the search engine actually computed to the observed clicks. With a tiny corpus, you can validate the pipeline before you scale to thousands of queries. Think of features as numeric fingerprints the search engine computes while answering a query. A BM25 score on the title is one fingerprint. A popularity count is another. Feature logging captures those numbers for each document the engine considered. Clicks are the ground truth signal. By joining them, you convert behavior into labels. Strengths: it is faithful to the engine and reproducible. Weaknesses: click noise and coverage gaps need careful handling. Next, we will register a reusable feature set on the server. This example configures a learning to rank feature set in OpenSearch using the LTR plugin endpoint via client.transport.perform request. The variable fs declares fs1 with one feature named BM25 that accepts a parameter q. Its template is a match query on the title field. So during searches, the plugin can compute a BM25-based feature tied directly to the query text. Posting the definition stores it server-side for reuse in queries. The printed features defined value confirms how many features the set contains, validating that the feature store is ready to log vectors. Knowing there is exactly one feature clarifies our initial minimal feature space. Now we will run a search that asks OpenSearch to log the per document features for a query. This snippet issues a search that activates the OpenSearch LTR plugin by adding an SLTR rescore referencing the FS1 feature set. The variable to passes the query text apple through the params map, and ext.ltr log requests per document feature logging. The client.search call executes the request, returning hits that now include an LTR log field with feature values. The dictionary feat is built by extracting and rounding the BM25 metric for each document, keyed by document ID for easy joining later. Increasing window size would log features for more candidates at a small latency cost, while decreasing it reduces both coverage and cost. The printed vectors logged count confirms we captured feature vectors for all results. Next, we will simulate user clicks and turn them into labels that match the logged vectors. This snippet simulates user feedback by defining a tiny click log keyed by the query Apple. The variable clicks records multiple clicks on document 2 and 1 on document 1, indicating engagement. The dictionary Y assigns a binary label per document in feet, 1 for any clicked document and 0 otherwise. This aligns observed behavior with the feature vectors we logged, forming the core of an LTR training row. If you require stronger evidence, raising a minimum click threshold would reduce positives and emphasize more confident labels. The printed label's positive value shows how many documents will be treated as relevant for this query. Now we convert those labeled feature rows into the classic training format many rankers expect. This example converts labeled feature vectors into a classic LIBSVM style format used by many LTR pipelines. The variable rows encodes each document as label, a query ID, QID, and the first feature 1 with its value, plus a trailing comment of the doc ID. Sorting by document ID keeps the output deterministic, and the split into train and valid demonstrates a simple, reproducible partition. In practice, you would write train and valid to files and add more features as 2, 3, and so on. The printed export lines count confirms how many total training rows are ready for downstream modeling. This toy flow maps cleanly to a real system. The same steps run on larger corpora, with more features and a more careful click aggregation step. The only difference is scale and the need to manage storage and throughput. Recap: what it is: a pipeline that logs engine features and joins them to clicks to form ranked training rows. When to use it: when you want training data faithful to what the search engine actually computed. One caveat: clicks are noisy and need thresholds or smoothing to avoid bad labels. Wrap up punch: a practical next step is to tune the BM25 parameters that produce the TBM25 feature, or to add a second textual feature, then re-export and compare model quality. If short, practical IR helps, subscribe and watch the IR videos.